Yes. Yes. Okay. So the greatest integer function, okay, if you have a function that looks like this, f of x equals, and then you have this funky looking bar thing like this. Okay. This is going to be a step function, a piecewise step function. What happens is your domain of this function is negative infinity to positive infinity. Your range is the set of integers, okay, is the set of integers, because we have to figure it out from there. Set of integers. Your x-intercepts, okay, your x-intercepts are in the intervals at 0, 1. Your y-intercepts are 0, 0. Your constant between each pair of consecutive integers and jumps vertically 1 unit by each integer. So if I graph this, a step function would look something like this. And have a closed dot, an open circle, there's 1. Closed dot, open circle. And it's going to keep going like this, like it's a stair step. And this one would be open circle, closed dot. So it's like it's taking steps up, okay? That's why it's called a step function. Because of the vertical jumps described in this graph, the greatest integer function is an example of a step function, okay? It is a step function. Whose graph resembles a set of stair steps. Some values of the greatest integer function are as follows. Your greatest integer is less than or equal to -1. Your greatest integer is less or equal to -half, and it keeps going on and on. Now, we're going to take this information, and from there, we can graph piecewise functions. So if I have a function that says f of x, and then it has equals, and I have two equations, 2x plus 3, where x is less than or equal to 1, and negative x plus 4, where x is greater than 1. Okay, how do I put those in my calculator again? What do I need to do? Okay, one on the y line, y1, one on the y2 line. But you also have to make sure that you put this in with it as well. So you're putting parentheses around the 2x plus 3. And then you're doing parentheses again, and you're saying x is less than or equal to. Where do you get the less than or equal to?
Second math.
Less than or equal to 1 in parentheses, and then I go down and drop the other one in. Negative x plus 4. And then I say x is greater than 1. And I press graph.
That's supposed to look like that.
It's supposed to look like a what?
Hook.
Like a hook?
Mm-hmm.
So you have one that looks like this. So you have one that looks like this.
That's stepfather.
Okay, On this one, your dot is going to be closed. On this one, your dot's going to be open because of how it's graphed. Okay, so on the first one, 1, 2, 3, 4, you're going to go, and that first circle is going to be up at 1, 3. And it's an open circle, and your line kind of veers off like this 3, 4. On your other one, your circle is closed at 5, 1. And this graph goes through 3, like that. So you have those two graphs on one. You have a piecewise defined function. Okay, make sure that you know when to use a solid dot, when to use an open circle. Then we have to talk about if a function is even or odd. Okay, a function whose graph is symmetric with respect to the y-axis is considered an even function. A function whose graph is symmetric with respect to the origin is an odd function. So if I have a graph that looks like this, if I have a parabola, okay, that is symmetric to the y-axis. So that is an even function. If you have a graph that looks almost like a like that, okay, that is symmetric to the origin. That's considered symmetric to the origin. If it is symmetric to the origin, then it is an odd function. And then you can have a graph that looks like this. Okay. And that is symmetric to the x-axis, so it's not a function. Because if I did the vertical line test, it would go through twice. Okay. So you have 3 different styles of graphs that we're going to have to classify as an even function, an odd function, or neither. You're going to look at problems, and you're going to plug those in your graphing calculator and then solve. That